estimation. So I'm assuming that there is not any familiarity, and we'll start from the basics. So what we will do is we will talk about how do we model key points. Uh, so how does key point estimation work? We'll also talk about the data. I mean, we have the model, right? We have something that in deep learning that does the modeling for us. But how do we build the underlying data on which this model will work? And finally, there'll be a short Jupyter notebook demo in which we'll just understand how this key point estimation thing works. So yeah, that's my photo before the pandemic. And like I was introduced, I am a research engineer with Mercedes-Benz, and I basically work on the interior assist program. So I'll come shortly to that. I have, like sir mentioned, some publications in this topic. So let's quickly dive into. Imagine you are an engineer with your favorite automobile group, right? I may have my biases, but I hope you can just imagine, that you are an engineer with your favorite automobile group, and your task is driver monitoring and passenger monitoring systems. So when I say driver and passenger monitoring, what I mean is that someone is driving the car, right? How do you do drowsiness detection? How do you note that the driver has his hands on the steering wheel? How do you know that the driver is not distracted and he's not looking elsewhere and he's looking directly at the road? Or it could also be safety critical applications. For example, a driver wants to open the door, the car door, or the passenger wants to open the car door, but a car or another vehicle is coming, from the other blind direction. So can we trigger warnings that when the door is not safe to open, the driver or the passenger should not open the door? So as you can guess, right, that most of these things rely on in-cabin perception, and that is what I do at Mercedes, and that is what a lot of automobile groups also are focusing on. How do you identify various movements inside the vehicle? Now, naturally, we are talking about humans, right? So in a car, we have occupants mainly as humans. So one way to analyze this movement is basically through understanding what the person is doing. So given the person, the task is to basically estimate key points. So you have the head key point, you have the neck, you have the shoulders, you have the uh, uh, elbows, you have the wrists, and so on. So one task could be estimating the key points corresponding to the person. Other tasks also include estimating key points corresponding to the hand. I'll just minimize this once again. Right. Uh, one could be identifying the person, one could be identifying the hands, one could be identifying the face. So based on this, you can also do a lot of things like recognition, activity recognition. Is this person walking? Is this person sleeping? Is he trying to lift something up? Or like this demo from MediaPipe. It basically shows various kinds of hand gestures which could translate to different kinds of actions. You also have face identification, like if in your smartphones, right? You maybe lift up your smartphone and you get it unlocked with your face, so face unlock. So those things also work on key points for the face. So the main essence is that key points are very useful, and they are basically a scalar quantity. So by scalar, I mean you can represent that as a u and a v. So given an image, the task is to estimate u and v value corresponding to the key point. So any questions still here before I go on? What exactly is key point estimation? Okay, then I assume everything is clear till here. So some examples, in a bit more in terms of how architectures are developed to do this. So you have synthetic images. For example, the top row here are real images, the bottom are synthetically generated. So you could have real and synthetic images, and then you have some deep learning model that either regresses key points, that is the u, v, or x, y, z values. In terms of human pose, it is u and v. In terms of hand pose, it is x, y, z. So here you are estimating not only the spatial coordinates, but also the depth. In terms of human pose, what we will talk about is estimating just the u and v coordinates. So these are the various tasks that you can do in key point estimation. And most of it is basically dominated by human pose. So let's talk a bit about how we model this. So like I said, right, a human pose estimation is that given an input image, you are basically trying to estimate the person's joints. So you could either use temporal information or you could use scalar information to do that. And the idea is that the network should be lightweight. That is, it should not be very big because big networks take a lot of time to run also. So the smallest network that can give you desired levels of accuracy. So this is the task of human pose estimation. Now we'll quickly just go through what deep learning is and basically how it's transition. I'm sure everyone must have heard about deep learning, but just a quick refresher. So you have uh, before the deep learning era, you had some inputs, you had some fully connected networks, and you had some outputs. This was the neural network paradigm for quite some time. The thing was, this was good for tasks where you don't have spatial relation in the input. For example, let's talk about number two. How do humans assess that this is number two? The fact that you can make out, right, that these black pixels are somehow related and somehow they are forming a structure together. Now, if you just flatten this out, that is, instead of considering it as an image, you consider it as an array, a very long array of vectors, you are losing out on the spatial information. And this holds true especially for key points, right? Because for key points, you don't need to look at just the entire image, whether it's containing a person or not, but you're also trying to guess where the next key point is, given the current key point location. So a lot of the spatial information would have been lost in normal, in fully connected way of doing things. So that is why you have something called as convolutional neural networks that help us in using this spatial information to give better outputs. Now, the idea of convolutional filters is quite simple. In terms of image processing, these are basically, you can consider them as kernels, as filters. They pass over the image and they give some kind of an output. And as you go deeper and deeper in these convolution layers, uh, uh, the view of the network increases. So maybe the first convolution channel may see a very small part of the image, like they show this box here. But as you go deeper and deeper, the view increases almost to the view of the entire image. And this is how final decisions are made. That you learn local features, small features initially, and then you learn these deeper features. And this training is done through an algorithm called as backpropagation, where we compute a loss over our output and we adjust the weights such that we minimize the loss. So let's talk about how we do things with humans. So I'll come back to this slide later. First, maybe I'll look at a simpler version. So let's say that we have an input image, right? We have an input image, and maybe the most naive way of estimating key points is give this image to a network, and that network will basically give some kind of an output. So for example, if you want the right elbow and the left elbow locations, give the input image through the deep learning network and ask it to predict these output values. Now, this particular architecture, as they call it, deep pose, was one of the earliest ones. It came out in 2014. So the way of doing things is a bit different from how we do it now, but nevertheless, it's still useful to know how this has evolved. So given an input image, you try to regress the targets relative to the bounding box. But the problem was that now when you're doing minimization, right, of the objective, uh, like for example, this is also an E, this is also an E. When you're trying to minimize the objective, because it can't allot one knee here and leave the other one knee there empty, it will try to find an average of both. So when it tries to find an average of both, you find issues. And the next thing is that uh, having direct point estimates for key points, they may not be the best way to reflect our knowledge about how human joints are. For example, what I mean to say is that let's talk about the elbow joint, right? If the elbow joint is located here, does that mean that the elbow joint can't be located here? I mean, there is a tolerance, right? What we say is that we know that the elbow is somewhere here, or this entire part is an elbow. So having these scalar estimates for the elbow is not really the best way to work. So these were the two major drawbacks which led to the development of our next architecture, which is quite commonly used nowadays. So any questions with this particular architecture here on how things are done? You have an input image, you have some convolution, then you flatten it and you directly regress XY values. Drawbacks: XY value are point estimates and they don't really convey the ambiguity with a joint, right? Like I said, a joint could be any of these pixels, not necessarily one single pixel. And the second drawback is that it tends to average out to find the correct uh, value that minimizes this particular objective. So to circumvent that, what uh, how the community moved is that they considered heat maps. So now we don't have single scalar values like 0.45, 0.12, 0.98. Instead, we plot these nice Gaussians and we tell the model that, you know what, this is the joint. These particular corresponding parts are the joints. So the architecture remains pretty much similar. There are a few key changes. First is that it remains a convolutional neural network. You have an input image and uh, you pass it through these R glass. So it's called stacked R glass because it's R glass 1, R glass 2, all the way to R glass n. And each R glass is basically a structure like this. This is quite simple. What it does is that given an image, it will try to produce that image at various scales. So this scale could be something like minimizing and continuously minimizing till the smallest scale, and then again increasing it in size. And this we do at multi-scales. So for example, with the largest scale here, we retain this largest scale and produce an output here. As we go smaller, we try to retain the smaller features also and produce here. So the entire idea of this stacked R glass is that uh, we have features at multiple scales, and the network then tries to determine what scale is useful for the particular image. So any questions here? I assume this will be more visually appealing because it makes sense, right? It tries to say that the joint is located in some area. We are not giving a single estimate, and that the network will then try to predict what we call as heat map. The difference with the previous approach is instead of a scalar quantity, now you will tell the network to predict a heat map, which is the rectangle. Within that heat map, where the joint is located, there you have a Gaussian. And for each joint, you have its own set of Gaussians. So if there are 16 joints, 16 Gaussians, and the neural network is expected to regress this. So is this part okay? I'll go ahead then. Right. So previously we saw that there was this particular architecture which allowed, one second, sorry. Yeah. Previously there was this architecture that looked at images at different scales. But the problem was it did not allow features from different scales to directly interact with each other. And this was something remedied by this high resolution network. You have an input, again, you pass it through a deep network, you get some initial set of features, and then each feature, you basically try to have them interact together. For example, here. When these features start interacting with each other, you have representations that look at the larger image as well as the smaller image. So these big boxes, right? These big boxes are outputs of the deep network. So they look at images at a smaller context, whereas the smaller boxes, they get to look at the image in a larger context. So having this small and large view interacting with each other allowed the network to become much more expressive and to learn much better things. So this is currently one of the high performing networks for human pose estimation. But then this also has one small issue, that these are very, very big networks. We are talking about networks that have millions of parameters. So in comparison to that, the stacked hourglass may not perform state of the art, but it is at least small enough that it can fit into our devices and still give us reliable estimates. So whatever demo that we do later will be based on this stacked hourglass. Right. So maybe I'll just quickly show, 1 second. Uh, I'm sorry, I'll just minimize this thing here. Yes. So we'll just look at it through a demo. I'll move this here. Yeah. So from perspective of a demo, right, we want to visualize whether whatever we've said, is it really corresponding to the correct thing? So there are two steps that we described. First is the input image, for which we want to estimate the skeletons. So for the skeleton, we try to plot these particular key points as a true value. So now what we are telling a network is that it has to regress a 64 cross 64 box with a Gaussian for that particular joint. So this is what we tell the network. We'll go through these images one by one later. We'll come back to this. But then this is how our output will look. This is what the network predicts. It predicts the head. It predicts, this is the network's estimate. This is what the network learns from our images. And then we draw a skeleton, and this is what the network predicts. So this Jupyter notebook, we'll come back to it again later, but it's plug and play. You can basically try out and see a lot of things. You can even discuss various failure cases like this one. This is where the network gets confused between the left leg and the right leg. So we can talk more about this after we return from the presentation. These are another few failure cases. But this is basically the idea of human pose estimation. So there are a few more fancy ways of achieving this thing. And this particular architecture, open pose, it basically worked for images with multiple persons. So far, we've looked at images where there's a single person, and we've not talked about multiple persons, right? So this may appeal to some computer science students because they use computer science techniques, which I'll shortly describe. But the idea is that we have key points, but we don't know which key point belongs to which person. So how can we identify which person is associated with which key point in a way that the computer can operate on it, right? As a human, I can identify key point 1 belongs to person 1, key point 2 belongs to person 2. So how do we get the computer to understand this? So this paper called Open Pose, they came up with two things. One is something they call the part affinity field. And the second thing is what they do is called bipartite matching, which is a very common computer science algorithm. So with part affinity fields, they basically try to find out how one part is related to another. And this is based on simple geometry that given, one of the key points is here. And the same person's key point is maybe x2 here. So we will try to predict a field, a vector. So given x, that is the key point 1, given key point 2, we will see which are the how to generate a field from xj1 to xj2. So, and this is how the field looks like. So for any point that lies within this particular joint, there is a field. For all other points, there is no field. So for example, if we are talking about two joints here, right? This is the elbow joint. So we know that the elbow joint, the wrist for this elbow is not going to be here because the affinity field for this particular joint is up. For example, shoulder to elbow, the shoulder says that the elbow is located somewhere up, and this particular person's shoulder says that the elbow is located somewhere down. So you have these kind of affinity fields that the neural network predicts. Now the issue is that we have these fields, but we still have values, right? What I can say is that green belongs to blue, maybe with an X value, and this green belongs to this blue, maybe with some Y value. Is there an algorithmic way that given all sets of joints, we can assign an entire set to a person? For example, given the red, green, blue, how do we know that it is not red here, the shoulder, the green here of this person's elbow, and the blue wrist here? So here what we do is we try to solve it using something in computer science called bipartite matching. That is, assign the particular joints as one side of the graph, the other joints as another side of the graph, and find the linkage that results in maximum value. So for those interested, maybe you can look at something called as bipartite matching and the Ford-Fulkerson algorithm, the max flow algorithm. So the idea is that the computer can use these part affinity fields, the value produced by them, as well as what all joint configurations are possible, to come up with the best estimate of which joint belongs to which person. So at the end, when you have multiple key points, there is no confusion as to which key point belongs to whom. Is this okay? So I'll go back to the first algorithm also. Again, this is quite a traditional one, but still worth discussing. Is that they use probability graphical fields, probabilistic graphical models. What they say is that it's a simple model that we know that the shoulder depends on the face, the elbow depends on the shoulder, and shoulder depends on the elbow, right? This in literature is called a Markov random field. So given this particular graph, can we refine the estimates of shoulder and elbow given the face joint, given the shoulder, given the elbow, given the wrist? So the idea is that beforehand, we compute the relation between the shoulder and face, the elbow and shoulder and wrist and elbow. Once we compute this relation, then we try to plug in whatever the model is predicting. So for those predictions where the model is predicted aligns with what we have previously computed about how the relations have a high energy, you have some key point estimate. If it falls within this particular uh, prior knowledge, then it has a very high output value, and therefore it is the correct prediction. So deep learning that rely on predicting joints for multiple persons and finding ways to estimate which joint belongs to which person. And there are can be refined the what the network has predicted. Projection that matches the 2D the most, and then use that depth value as a pseudo metric for the depth. So you get UV from the 2D estimation and the depth from this 3D value. There are also some other approaches that basically that to reliably estimate depth. Particular approach, what they do is that the same person They've got n cameras at different viewpoints. So using that, they get 2D estimates like what we've seen previously. And based on these 2D estimates, they then try to do something called as triangulation. So a triangulation is basically converting that 2D into a 3D ray, seeing where those 3D rays intersect or where the distance between those 3D rays is the minimum, and the place where that 3D ray is the minimum is the depth value. So that way you can go from XY, from UV to XYZ. So this is something that they picked up from stereo vision. This is something, these particular 2D to 3D approaches, they use a simple depth network, or they do some kind of matching. So one small thing before we proceed is, for classification, you have standard accuracy, you have precision, you have recall, but similar things cannot directly work for human pose. So what we try to do is that, uh, given the ground truth, we try to assess how close the prediction is with respect to the ground truth. Again, I mean, when we talk about human pose, we are also talking about the scale of person. For a large person, the scale is much larger in comparison to a smaller person. So then we also have some kind of a normalizing thing. So this percentage correct key points, what it does is it checks how the ground truth and the predictions are close with respect to some kind of a normalizer. So let's say that the head is located here. Our prediction is of the head is somewhere here. So given that the distance is small with respect to some normalizing constant, uh, we say that the network is doing a good job. But for example, if the head is here, where the actual head is located, the ground truth, but we predict the head somewhere near the ankle. Now this distance is very large with respect to some normalizer, and therefore the network has not correctly identified that joint within the given distance. So to assess human force models, we tried to plot how many of the joints have been identified versus at what normalized distance they've been identified. So as you increase the distance threshold, more and more joints will be under that distance, right? So your value keeps increasing, and smaller means how precise it is. That the displacement between the true and the predictions is very low. And therefore, if a model has a very high PCK at very small normalized distance, that means that the model is very, very accurate. So any questions here? So I'm assuming no questions. So maybe I'll just take a short break and we'll go back to the demo. So how do you do all of this in code, right? Basically, there are some few key ingredients that you require. You require a data set, and you require a model. So the model that, as we have discussed, what we will be using is called the stacked hourglass. So first we import the stacked hourglass model. We also have HRNet, but HRNet is not something that will work on my computer. For that, I require whatever maybe my employer provides. But for our setup, right, for personal use, we can use hourglass, which works as well. So we import hourglass, and we also import a data loader using different kinds of data sets. So for human pose, basically, there are two data sets. One is MPII and the second is LSP. And when I say human pose, I mean single person human pose estimation. So for a single person, that means that image has only one person, like the images that we see here. In single person also, we are talking about estimating the key points only for the person in the center. Like we saw, right, in one of the approaches, they try to predict key points for multiple persons. But for now, we'll stick to predicting the key points for the center person. So you have the model, you have the data loader, and you also have some